Okay, I'm Mr. Baggett. I'm teaching the engineering class here, and today we're looking at the structural testing of simple beams and the flexure formula. So I've got a lot of stuff on the board here. I want you to take notes as I go. I didn't want to write the notes because my back would be to you the whole time. So just pay attention to what I'm talking about. The first thing we're going to do, and this lecture on simple beams really relates to the truss bridges you're going to build and test later on. So I want you to get this concept. Now, this is a whole class in itself, really. This is a class that you could spend hours and hours and hours on. We're just introducing this topic of testing of simple beams, okay? So here's the deal. Wood is an elastic material. Okay, here's a pine beam. Okay, I can bend it. Okay, I've made the beam fail. All right, so it's kind of what we're going to talk about. We're going to talk about this graph and what stress makes it fail. How much stress makes it fail? Okay, here's some simple beams up here that we've tested up at our local college, Humboldt State University. So this is a beam that's simply supported on both ends. It's a simple beam. It's loaded like this. We use a universal testing machine up there at HSU. The dial indicator is keeping track of the deflection. We take the data, and then we can do some fairly sophisticated calculations to kind of define this material. Here is another pretty amazing thing. This is an arch bridge. Hopefully you guys are learning about the different types of bridges in this unit. This is an arch bridge. As you can see how simply these pieces just fit together. We loaded this bridge on the universal testing machine too. It held 4,320 pounds and didn't fail. The only thing that failed was this. You can probably see it failed in compression on the top. It failed in tension on the bottom. It was creaking and cracking. 4,320 pounds. That's a lot of weight. So anyway, wood's an amazing material. So in this little unit, you're going to do a structural test of a simple beam. Your instructor will give you a simple beam, and there's another video I've done that kind of shows this test and what you're going to be doing there. So anyway, today I want to start with what we've got on the board here. And I got these a little out of order, so start taking notes. So I want to talk about first stress and strain. Okay, this is very key. It's a very key engineering kind of concept, especially when we start building bridges and houses and floor joists and all this kind of thing. So stress is load acting on a unit area. There's a little drawing of that. I've got a load that's pushing down on this beam. Okay, so it's load acting on a unit area. So load, variable P, area, variable A. So I'm just making up some numbers here. So we're putting 2,000 pound load on an area of 4 inches squared, which would calculate out to be 500 pounds per square inch, PSI. I'm sure you've heard that term, pounds per square inch. So that's stress. Okay, so did I just stress this beam? Yeah, big time. I just stressed this beam. Did we stress these beams? Yep, big time. When we did them, you could hear it. Again, creaking and groaning. Okay, strain. Now, these two are very related, stress and strain. So strain is unit of deflection per unit of length. So if I measure my beam, how long it is, I know what load I put on it, and I've made it fail again. It's a pretty weak pine beam. Then I can pay attention to what kind of deflection do I get. How much does the beam bend when I load it? Okay, so stress and strain very related, which is Hooke's law. Okay, again a classic engineering kind of concept. Hooke's law: stress and strain are proportional. Okay. You could actually write down for Hooke's law, for every unit of stress, there's a proportional unit of strain. I don't have this up here, but I'll say it again. For every unit of stress, there's a proportional unit of strain. When we get to this graph, that's what this is all about. You know, this slope is showing you Hooke's law. As I stress something, it's going to also be strained. Okay. Now, in my little terms up here, I would want to go next to modulus elasticity, which is kind of what we really, again, this is a whole class in itself. A very deep kind of topic. I've actually included in this course 2 videos from a professor at UOP who gets into the kind of the calculus side of this whole thing. I'm just introducing this just in a very cursory way today. So anyway, we want to look at the modulus elasticity of when you do your simple beam test, you're going to actually calculate what is the modulus elasticity of this piece of wood that you've been given. So what the modulus elasticity, also called Young's modulus, measures is the ratio of stress to strain in the fibers in the wood along the upper and lower surface of a beam. So as I stress this beam, the modulus elasticity is going to tell you what is going on in the stress and strain in the fibers at the very top and very bottom of the beam. Okay. Again, you can see this one shows it better. You can see as I stressed this beam, I loaded it. It failed in compression. You can also see, hopefully you can see at the bottom, it failed in tension. So these fibers are just completely pulled apart, right? So that's kind of what we're talking about. So if you know the modulus elasticity of a material, that's going to tell you, can I use it in my bridge? Can I use it in building my house for a floor joist? Okay, so it's a very important value. Okay, there's charts, and you're going to be given a chart in this thing. I hand out, your teacher will hand out a chart which just charts it. For oak, here's the E value. For pine, here's the E value. For Doug fir, here's the E value. So modulus elasticity is a very important thing. All right. There's also, you're going to be handed out. Well, let's get over here first. Okay. So now this kind of launches us into the flexure formula. Okay. Again, a classic engineering formula. Okay. So the flexure formula for the modulus elasticity. Again, the variable for the modulus elasticity is E, so it's stress divided by strain, or now we start putting some real values to it. So E is big K, and we'll talk about these constants. There's a big K, which is a quarter, and there's a little k, which is 1.5. So we'll talk about that as we develop this. So anyway, the modulus elasticity is K times P prime L to the third power divided by Y B D cubed. So that's the flexure formula. We're gonna derive that formula to, and you'll be handed out this handout as well, where we can take the flexure formula and then we can find from that we can calculate the modulus of rupture, how much, the maximum bending stress sustained at failure, like I just demonstrated. Okay, what is the modulus of rupture of this material? Okay, we can calculate, start with the modulus elasticity, which is really, modulus elasticity is a measure of the stiffness of a material. So this is not terrible. This is going to be a low modulus elasticity, this pine. I've broken it twice now. What if I take this oak beam? It can be higher E value or lower? Higher, much higher. This is going to be much stiffer beam. So the modulus elasticity is really a measure of the stiffness of a beam. As you calculate this out, and you'll be doing this, you'll be collecting your own value. You'll have a value for P. You'll have a value for the length of the beam, for the deflection of the beam, for the width and depth of the beam. You're gonna measure all this, have all your data, and when you calculate this out, this comes out to be a huge number. It's like 1.2 times 10 to the 6th. It's a big number. So that's not an actual stress in the wood. It's just a number that gives you a relative sense of how stiff is this beam. All right. So now draw this picture. Okay. Draw this little picture of a simple beam. All right. So I should label this picture. This is a simple beam. All right. So we just have a beam supported just like I have up here, and this is what you will really do. Hopefully I don't know where you guys are in the country looking at this, but hopefully you can get to a university or community college or engineering firm or something that has a universal testing machine, which will give you some real data. If you can't, I showed you on the little video how you can load your beam with a bucket of sand, and we can still get some pretty good data. But we get a lot better data with the equipment that engineers really use to do this kind of thing. So if you can use a universal testing machine, I would do it. So anyway, we have a beam, simply supported. There's a neutral axis, which is very important in the beam. The neutral axis runs, through the center of the beam. We'll talk a little bit about that. So now we start putting some variables to this. So this is the length of the beam, L. The depth of the beam is this. Okay, that's the depth of the beam. The width of the beam is this way. So if you're looking at this beam, okay, length of the beam, the length has to be between supports, okay? And then we've got the depth of the beam and the width of the beam. So when you are doing your experiment, you're going to take a dial caliper. Hopefully you guys have dial calipers. And you're going to get these measurements just as accurately as you can, okay? I've noted here that we're doing this in inches. So we're doing the length in inches, the width in inches, the depth in inches, all right? Could do it in the metric system, slightly different units. Most of the textbooks, like we use a uniform building code. I don't have it here, but that's all in inches, so that's why I'm doing it here. So anyway, this is a drawing of a simple beam. Now, when you load the beam, okay, I'm gonna go ahead and load the beam. So we put a load on it. Okay, this is value P equals load. We're going to be taking notes. We'll collect these and grade them. So this is the load, and this is going to be in pounds. All right. As I load this beam, okay, I'm loading the beam with the universal testing machine or with a bucket of sand or with whatever you want to load. If it's your house and you're going to be walking on the floor joist, you're going to load this beam. Okay, as you load the beam, it starts to deflect. Okay, so we draw this dotted line like this. Okay. Okay, so this drawing becomes a mess now. But the beam, just like I demonstrated with this pine beam, it deflects. As I load it, it starts to deflect. All right. So we want to start collecting the data when we test this. How much did it deflect? So this little, I'll do it in red. This little distance here it is variable y. Okay, small y, and that's deflection. Okay. So we want to keep track of that. The best way to do it was the dial indicator, again, to thousandths of an inch as accurately as you can do it. We're going to try to match your data, like your teacher gives you a pine beam. You do collect all your data, you load the beam, you do your calculations, and you should be able to verify that the E value, the modulus elasticity, this pine beam, go to the table that you're going to be handed out, or you can look it up online, or they're in a lot of books. Just open the book and say, did my data match the E value of the pine beam that they did? Now, you should, if you measure things, accurately. And the problem with doing it with a bucket of sand is knowing exactly what the load is going to be a little iffy. But you should be able to get a value pretty close to the table values of the modulus elasticity, whatever material you're given. Okay. So this is the simple beam. Now the last thing I want to talk about here just for a second is that if we graph this data, the stress strain data, okay, again we load the beam. That's stress in pounds. I'm loading this beam. Okay, it strains the beam, so I'm going to record the deflection again. Okay, so we got, and I haven't put any numbers to this graph, but you could say this is in inches, and usually, usually this is in thousandths of an inch, because wood is a very strong material, like I've said. So if I start loading this beam, I get to 1,000 pounds. The beam's only deflected a few thousandths of an inch. It hasn't deflected very much. So when you guys do your test in your classroom, you certainly can't do it with a beam this size. you can't try to load this with a bucket of sand, because you could put a lot of sand on here and it's not going to do anything. So the beams you're going to be given are fairly small beams, so that we can load this beam with an appropriate amount of sand, so we don't have to use 10-gallon buckets of sand. So anyway, we graph the data, the stress strain. Again, I said this earlier, this slope of the proportional range of the material is the modulus elasticity, and it's for every unit of stress, there's a corresponding unit of strain. Hopefully you understand that. Okay. Now there's several things going on in this graph, and this could be the graph of real data. You could take the beam that you test and graph this data, and that's the advantage of using the universal testing machine, is that it will tell you when the material has reached the proportional limit. So that's P prime. And what the proportional limit is I can load this beam, stress it, and it deflects, and flex, and if it returns to its original shape, okay, I haven't got the proportional limit yet. At some point, you reach a point of no return, where I've stressed this beam to the point where it hasn't failed yet, but it's not coming back to its original shape. Do you understand that? And when that happens, that's the proportional limit. You've kind of reached the limit where this beam cannot be stressed anymore. Okay. If you go on beyond the proportional limit, like I just demonstrated, and I'll do it again, and I get to the P max, which is the load max. Again, variable P. Okay, variable P as load. So once I get to P max, okay, it's to now that's modulus of rupture. Now we're down here on the ground. But just before that point, just before that happens, I've torn some fibers of the wood. I'm well past the proportional limit. It's not like I've just deformed this to the point where it's not coming back. I've now got to the point where I've actually broken some of the fibers, and now the graph falls totally off, and you've ruptured the material. Okay. Again, this is a very introductory talk about this whole concept of the flexure formula. We'll have one more short video on demonstrating a few of the calculations, and then if you want to take this farther, I've included 2 videos that again are calculus based, and they show you what engineers would really do with this data, and they're actually very good videos. It would be, is your math background up to that? So that would be your teacher's decision whether or not you look at those videos. So thank you very much.